Hi everyone, welcome to section 2.2. We're talking about infinite limits and limits at infinity. Our goal is to find limits of functions as they approach infinity. So let's look at some of our properties and definitions to get us started. Limits of power functions at infinity. So we're looking at the limit as our variable goes to infinity or negative infinity. So we're really looking at what's happening to our function as it goes off into the positive infinity, as it goes off into negative infinity, what's going on. So number one, we're looking at the limit of k over x to the p, and we're given that p is a positive real number, k is any real number except 0. So we have a number over our variable raised to a power. And if we look at what's happening as x goes to the negative infinity of something that looks like a number over x to a power, it's going to go to 0. If we look at what's happening to that function as it goes to positive infinity, it says it's going to go to 0. Then we look at what if it's not in the denominator? What if we have the product, k times x to a power? As it goes to negative infinity, it will go to positive or negative infinity. And as it goes, if we look in the positive direction, positive infinity, we're looking at, okay, it's going to go to positive or negative infinity. And if we take a step back and just think about that, we're looking at, okay, in these examples, my denominator is getting bigger and bigger and bigger and bigger. Well, yeah, that means my fraction is getting smaller and smaller. It's going to 0. So that makes sense for us. And in these cases, I have a number getting bigger and bigger and bigger and bigger being multiplied by another number. Well, yeah, it's either going to be a really, really big number or a really, really big negative number. So that's the general overview of what's happening here. Okay. Limits of rational functions. So now we have a function being divided by another one. So a polynomial over polynomial. If f of x equals a times x to the m plus a minus 1 times x to the m minus 1 plus blah, 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 all the way down to our constant over b times x to the n. So we have a polynomial over another polynomial, then the limit of this as it goes to infinity, we can just look at our first terms here as it goes to infinity. And we can look at our first terms as it goes to negative infinity. So that's a really nice definition that we have here, a nice property to use, so that way we can figure out a way to find that limit. There are 3 cases to consider. If m is less than n, so keep in mind we have our polynomial divided by another polynomial. M and n are our exponents. So if m is less than n, that means the exponent on the denominator is bigger than the exponent on the numerator. Then our limit going to infinity is going to be the same, equals our limit as it goes to negative infinity, which is going to be 0. If the exponents are the same, then we just take the limit of our constants, a over b. And if our numerator power is greater than our denominator power, then the limit will be infinity or negative infinity, depending on what m and n and what a and b are. So let's take a look at some examples. That way we can really hone in on what these properties actually mean. So problems 1 through 3, find each limit, use infinity or negative infinity whenever appropriate. F of x equals x over x plus 7. Okay, so first we're going to find the limit of f of x as x goes to -7 from the left. So we're going to look at if the value is substituted into our function. If we're plugging in, then we're going to get on the bottom, if we do the dumb thing, -7 plus 7 is going to give us a 0 on bottom. So we cannot plug it in. So we're just going to have to look at what happens around -7 and values that are smaller than -7, okay, as it gets closer and closer and closer. So really you're looking at, okay, well, if I'm going from the left, I want to know, here's how I do it. I go, okay, when x is -7, we get a 0 on the bottom, so I'm going to cross that out. But what if it's -7, or no, -7.1. So I would plug in -7.1 over -7.1 plus 7. I'm going to get -71. What if I plug in -7.01? So I'm getting closer and closer and closer to that -7, right? -7.01. Is going to be 701. Let's do one more. -7.001. $7,001. And we can see kind of what's happening here, which tells us, okay, it's getting really, really big, really, really fast. So our limit is going to infinity. Let's look at it from the right. Same thing. So -7, big X, we get a 0 on our denominator. But what happens if we look just a little bit to the right? So we go -6.9. -6.9 over -6.9 plus 7. So we get -69. We go a little farther, 0.99. -699. If we go one more, -6,999. So we can see that side is going to -infinity. Now we take what we know about limits, and if we generally want to find the limit as x goes to -7, we want to make sure our left-hand side and our right-hand side are going the same. And since they're not, this limit does not exist. Okay, let's look at another one. 4x plus 1 over x minus 5 squared. And we're looking at 5. So 5 from the left, when x is 5, well, 5 minus 5 is 0, so. But if we look at 4.9, 4.99, and 4.999, what will we get? Four times 1, 4.9, plus 1 over 4.9 minus 5 squared. 2060. And if we do 4.99, $209,600. And if we do 4.999, $209,600. So we can see this is obviously growing quickly to infinity. Next, we look at it from the right at 5. So we're looking at 5.1, 5.01, 5.001 as we get closer and closer to 5. Okay. So we get 2,140. $210,400. And 2,100,000. Oh no, 4,000. Okay. This one also going to infinity. So since they're both going to infinity and they're both going to the same place, then the limit goes to infinity. Okay, let's look at number 3. Number 3 says x squared plus 3x minus 5 over x minus 5, and we're still interested in 5. So at 5, we get a 0 on the bottom. We're not interested in that, but we're getting really, really close. So we'll do 4.9, 4.99, 4.999. All right. 4.9 squared plus 3 times 4.9 minus 5 over 4.9 minus 5. Looks like negative 337.1. $4.99 negative 3,487.01. $4.999 negative 34,987.001. So this is going negative infinity. Let's look at the other side. So from the right, 5.1, 5.01, 5.001, 5.1 gives us 363.1. 5.01 3,513.01. And 5.001 35,013.001. Okay, this one looks like it's going to infinity. And since our left side and our right side are not going to the same place, this one does not exist. Okay, find each function value and limit. Use infinity or negative infinity where appropriate. So now we're going to look at what's the value of the function at this point and what's our limit. So for f of 20, we're going to plug in 20 everywhere we see an x. So we've got 5 times 20 minus 3 over 3 times 20 plus 2. So that will give us 97 over 62, which is approximately 1.5. Let's see, 1.5645. We're going to do the same thing for 200. 5 times 200 minus 3 over 3 times 200 plus 2. So this is 997 over 602, which is approximately 1.6561. Okay. So what is this telling us? As we make our values bigger and bigger and bigger, x is going to infinity. What is our y value going closer and closer and closer to? Well, our property is telling us when the powers are the same here, we just have to take the coefficients. So our limit as x goes to infinity is 5 over 3. And if we do 5 divided by 3, it's 1.6 repeating, which is exactly what we were seeing happen. So that's really cool to see the property actually play out like that. I think that's cool. Okay, let's do another. X minus 5 over 3x squared plus 2x plus 2. So first we'll plug in 10. 10 minus 5, 3 times 10 squared plus 2 times 10 plus 2, which will give us 5 over 322. That's approximately 0.0155. If we plug in 100, 100 minus 5, 3 times 100 squared, plus 2 times 100, plus 2, it's going to give us 95 over 30,222. And that's approximately 0.0031. And our property, when the denominator exponent is greater than the numerator exponent, tells us the limit is going to go to 0. And we can see that it's getting closer and closer and closer to 0 as we make our x's bigger and bigger and bigger. Okay, next one is an example of our numerator power being greater than our denominator power. Let's plug in negative 10. So we get negative 10 cubed, 2 times negative 10 minus 1, 3 minus 8 times negative 10. This is going to give us negative 1,021 over 83, which we can approximate to negative 12.3. Now, if we go even more negative and plug in negative 100, negative 100 cubed, 2 times negative 100, minus 1, 3 minus 8 times negative 100 is going to give us negative 1,201 over 803. And that we can approximate to negative 1,245.58. Now, our property tells us when the numerator exponent is greater than the denominator exponent, it can go to positive or negative infinity. In this case, we could see it's going to negative infinity. Okay, find the vertical and horizontal asymptotes for the following functions. 8x over x plus 5. Now, how do we find our vertical asymptotes? We set our denominator equal to 0. So in this case, x plus 5 for our vertical equal to 0 means x equals negative 5. For our horizontal, we find the limit as it goes to infinity, because think about what's happening horizontally. So if we take the limit as x goes to infinity of 8x over x plus 5, our x's have the same power, which tells us we can follow the property and put the ratio of the coefficients, 8 over 1. So our horizontal is y equals 8. Those are our asymptotes. Okay, let's do the other one. 3x squared minus 5 over 3x squared plus 2. Remember, our vertical, we set the denominator equal to 0. 3x squared plus 2. 3x squared equals negative 2. X squared equals negative 2 over 3. And since we can't find a negative number and square it, or we can't square a number and get a negative number out, there's no vertical asymptote. Horizontal, we take the limit as x goes to infinity. And again, our x's are both squared. Our x's have the same. So we make a ratio of our coefficient 3 over 3, which is just 1. So y equals 1. Okay, our last example. Let's see, x squared plus 4x minus 5 over x squared plus 8x plus 15. So the first thing that we can do to make it easier on ourselves is to rewrite it, because both of these things we can factor. The top we can do x plus 5 minus 1. The bottom x plus 5 plus 3. And the x plus 5s will cancel, which leaves us with x minus 1 over x plus 3. Keeping in mind, x cannot equal -5 because we got rid of that one, but it's still there. It's still something that we need to account for. And we also don't want x to be -3 because that will make our current denominator a 0. So, vertical asymptotes. We have x plus 3 equals 0, x equals -3 is our vertical asymptote. Horizontal, the limit as x goes to infinity. Our x values, oh, that is not it at all. Our x's have the same exponent on them, so we make a ratio of their coefficients, which is 1. So y equals 1. And there we go.